Welcome back. So in the last lecture we derived the strong form for beam problem. Yeah, so we are into beam. So the strong form that we got was, either you can write it as d square m dx square plus q equal to 0, and this is in terms of m, but we also know that m equal to ei t square u dx square, where u is the vertical displacement. So if you combine them together, what you get it, d square dx square ei, then d square u dx square, okay, plus q is equal to 0. So this is the strong form we derived already. Along with that, what we need is the boundary condition. So boundary conditions. So as you know, it will have 4 types of things. So in beam, either you have the vertical displacement given somewhere, so u at some gamma u will be given. Let us say this is u naught. Then there may be the corresponding forces, or V, shear force. Okay, so V at gamma V equal to V naught. So this is shear force, may also be given. This is the vertical displacement. So what is V? V, as you know, V is equal to actually dm over dx. So okay, so V may be given, so V equal to dm over dx may be given, so that's what it is. Okay, now theta may also be given, so theta at, let's say, gamma theta equal to theta naught, let's call it. Okay, so this is the angle or slope of the beam. Theta, as you know, theta is actually du over dx. So you have to note basically theta, where theta is given, but where theta equal to du over dx. Okay, and the corresponding force is moment, bending moment. So m may be also given. So m at gamma m may be given m naught. So this is bending moment, may also be given. So bending moment. Okay, as you know, m equal to the equation how m related to u is given here, and accordingly you can find out how v will be. So if you assuming ei to be constant, v will be dm over dx, and m is given, m is like this one, so becomes ei dq u over dx cube. So this is what the v will be. Okay, so what we have is the boundaries, like we have gamma u, gamma theta, then gamma v, and gamma m. So remember, these are actually this gamma u and v relate to the degree of freedom which is the displacement degree of freedom. Okay, deflection related degree of freedom, whereas gamma theta and gamma m is related to the slope related degree of freedom. Okay, degree of freedom. So you should note that you cannot have the deflection, vertical deflection, and the shear force assigned at the same place. So they have to be different. Yeah. So they have to be either you assign the vertical displacement or the vertical force, that's a shear force. Okay. Similarly, the gamma theta and gamma m will not be common. Okay, will not have anything common, meaning that at the same point it cannot give both of them. You can combine this and this. You can give a displacement and a slope as well, that's possible, but you cannot give displacement and shear force, both is not possible. So remember those. Okay. So once we know what the boundary conditions are, basically you should also learn what is the meaning of that. Let us say if it is a beam like this, so this is simply supported both the sides. So here the u will be, so let us say this is x equal to 0, x equal to L, then we say u 0 equal to 0 and u L equal to 0. Okay. Now instead of this type of support, if you have like something like this one, okay, so then you will say u 0 equal to 0 and u, not u but theta 0 also equal to 0. Theta means slope, so that means du over dx equal to also 0 in this case. Yeah. Okay. There may be a case where you also have like this. Yeah. So in that case you will say here u L is also equal to 0. Okay. So there may be some force at the end. So let us say you have a condition like this one, like this. Okay, so this is F like this. So what will you do? Here it will be u 0 equal to 0, theta 0 equal to 0, and here v equal to will be v equal to 0, where v at L is equal to 0. What is the meaning of that? The v, as you know, is E I dq u dx cube at x equal to L equal to 0. That really means that. Similarly, if you have a bending moment applied here, m like this, so then you will say we know that m is E I d square, so say v m d square u dx square at x equal to L is equal to m. V equal to say f naught and m naught. So b equal to not 0. So we have given some value f naught, so here it will be f naught, sorry. Okay, so v equal to f naught. Here we are given m, so here it will be m naught, so m has to be m naught. So this value has to be m naught. Okay. Okay. So this is how you assign the boundary condition. Of course, all these things is repeat basically. This is the what you already studied when you studied the solid mechanics. So this is just a repeat of what you have done already. Again, if you are still confused about it, I advise you to go through the beam chapter in the solid mechanics book, okay, that you have studied during your second year classes. Okay, so now next thing will be once we know the strong form, the next thing will be to get the weak form. So what is the weak form that we want to find out? Okay, so weak form, as we have done always, so we will start with the strong form. What is the strong form? Strong form is d square m dx square plus q equal to 0. Okay, where m is the bending moment, q is the distributed load on the beam, and what we do, we always multiply it with a variable w, okay, d square m dx square plus q, and we integrate over the whole domain, in this case 0 to L, and we make equal to 0. Yeah. So this we have been doing for the bar case also. We had a strong form, and then what we did, we multiply by w, which is the weight function we called it, okay, and then we integrate over the whole domain and we make equal to 0. That really means we are going to minimize the error basically. Yeah. So once we have this one, next thing is to how to expand it further. So of course we have to know the property of w. And what is the property of w? This is valued for all w. W is any all functions which is, it has to be kinematically admissible, meaning that it should have a required smoothness. That's what is required. And what is property of that? As we said earlier, wherever the w is defined, so w at gamma u, that is where the u is defined, this has to vanish there. So this is the conditions, okay. And similarly, there may be theta also given. So in that case, dw over dx at gamma theta will also be 0, because both are equivalent. W will have the same dimension as the vertical deflection. So if the deflection is given, w will be 0, vanish there, and when the du over dx is given, then dw over dx is also 0. So this is the requirement, okay, on w. Otherwise w can be any kinematically admissible function, as we have discussed already about these, why these requirements are and all in the class. Okay. Okay. So we have the weak form which is in terms of w, then d square m dx square plus q dx equal to 0. Now we will do we will follow the same procedure that we followed for bar element. Only thing here is we have to do the integration by parts twice, okay. So here left hand side is equal to we can write in we can expand it, so w d square m and then dx square dx plus 0 to L q w dx. Okay. Okay, so not left hand side, say just expanded it, so total equal to 0. So now we take one of these, so this value 0 to L w d square m dx square dx equal to, now equal to 0 to L w d over dx, and here dm over dx and then dx, this. Okay, so that will be equal to, now we apply equation, apply integration by parts okay. So these things becomes equal to 0 to L, and then sorry we have w and then dm over dx, we have L0 minus 0 to L, and we have dw over dx, and then we have dm over dx. So we'll have this one, this is just by integration by parts. Okay, same thing we did when we were converting the strong form for 1 bar for the bar element. Okay, for the element which has the axial load only, so with the same thing we did there. Okay, so we have that, so that is equal to, now this is depending on if we had w given there, then sorry, if u given there, then we will make this thing equal to 0. If not, then accordingly we have to, then this will not vanish. So when u is given, this will vanish, and hence, so that really means we can write WL and dm over dx at x equal to L minus W0 and dm over dx. dm over dx is nothing but v. So if v is given or not, that's what it means. So dm over dx, x equal to 0, this. If w equal to L, if x equal to L, u is given, then this will vanish. Similarly, if x equal to 0, u is given, then this will also vanish, otherwise it will not. Okay, so I'm just writing like this one. Since I'm doing the general purpose derivations, so I will not actually make them 0. We will just let it be like this only, and then next term is minus, here you have 0 to L and dw over dx, then dm over dx. Okay, so let's write it where. So here we have the final, not final, but we have so far this expression. So say where, let's take this term now, let's expand it. So where 0 to L dw over dx dm over dx equal to Now we will apply the integration by part again. Okay, so integration by parts again. So where this equal to, okay, so again we can write in that form. So what the first thing will be this multiplied by m, so dw over dx multiplied by m, again this will be L 0 minus, okay, minus, and then 0 to L, and this will be d square w over dx square, okay, and then m dx. Okay. Okay, so again when we expand it, this one, so this becomes dw over dx at x equal to L times m at L minus dw over dx at x equal to 0 multiplied by m at 0, okay, and minus 0 to L d square w dx square m dx. So this value is for this one. So the combining them, what we get now is, so the initially we had this term, so we are talking about this term which is equal to these terms minus this, and this we have expanded further, okay, this, and this becomes equal to the whole thing from here to here. So we combine them together and we get del 0 to L w d square m dx square dx is equal to wl dm over dx x equal to L minus w0 dm over dx x equal to 0, okay, then minus expanded version was dw over dx x equal to L minus dw dx x equal to 0 m0, excuse me, here it should be m at L, okay, and then minus again here, and this will be 0 to L d square w dx square m dx, okay. So that will be equal to w x equal to L dm over dx x equal to L minus w0 dm over dx x equal to 0 minus dw over dx x equal to L multiplied by ml plus dw over dx x equal to 0 m0, and there will be plus 0 to L d square w dx square, sorry, here it should be dx square, okay, so d square w dx square m dx, okay. So this value becomes like this one. So the final form of the weak form becomes, so weak form becomes, so the first part, which is the second part, is 0 to L W Q dx, and then plus this, and everything becomes 0. So this plus is plus this one. So but this plus this is this, the whole thing. So we write this one, then we write this one. So 0 to L d square W dx square M dx, then these terms, so plus W at L dm over dx at x equal to L minus W at 0 dm over dx at x equal to 0 minus du over dx at x equal to L m at L, then plus du over dx x equal to 0 and m multiplied by m at 0. So everything of this becomes equal to 0. So this is the final weak form. Now let's put dm over dx equal to v and du dx equal to theta into this equation, and we will also expand m now. So instead of writing just m, we write m equal to ei d square u over dx square. So this we put here, and then we will have the final weak form. Okay, so final weak form will look like 0 to L wq dx plus 0 to L d square w dx square, and then m. So m is ei d square u dx square dx. So we got this one now. This we have, this we wrote here. Now the next term is this. So plus wl dm over dx is v. So we write v here. So v at L minus w0, and dm over dx is v, so times v0 minus d over dx is theta. So this is theta here, theta L, okay, multiplied by this one is m, so ml, and then plus d over dx is theta, so this is theta 0 multiplied by bending moment m0, and the whole thing becomes equal to 0. So this is the final weak form for the beam equation, for the beam problem. Only thing here is we had not actually applied the boundary condition yet, because this is for general purpose beam equation. So once we have the boundary condition, we can accordingly apply here, yeah, and then that will give you the final weak form for different problems. Okay, now once we have the weak function, the next step is to solve the problem. So in order to solve the problem, we have to know the shape functions. Okay, so shape functions. Okay, So we have to see the degree of freedom first. So as we have seen earlier, so if there are two nodes, 1 and 2, and each node will have 2 degree of freedom. So one is u1, this is u2. So these are displacement degree of freedom that goes up, and there is theta. So this is theta 1 and theta 2. So theta is the slope. So for example, this could be something like, the beam may be something like this one. So the slope of this will tell what the theta is. So theta 2 is like this one. This is theta 1, for example. Okay, so node 1 and 2. And then displacement, let's say you are measuring from the this is the baseline from where you are measuring, or with respect to any horizontal line. So let's say you are measuring with respect to this one. So this point from here to here becomes u1, and from here to here becomes u2. Okay, so theta 1 u1 and theta 2 u2. So the idea is to know the we have to write u, basically u x is a summation of n I x u I x. Okay, actually here u, instead of writing u, let's call it a small di. Okay, the reason is we are going to combine theta and u both. So let's not write u, instead of that we will use di. So what is the meaning of di? Okay, so here let's say this is I equal to 1 to 4, because 4 degrees of freedom. So 4 degrees of freedom. Okay, so what is the meaning of that is our n1 where, let's write here, where di, this is not di is a function of x, but rather di or d1, let's call it where d1 equal to u1, okay, d2 equal to theta 1, and d3 equal to u2, and d4 equal to theta 2. Okay, u1 theta 1, u2 theta 2. So that really means ux we want to define it as ux equal to n1x multiplied by u1 plus n2x multiplied by theta 1 plus n3x multiplied by u2 plus n4x multiplied by theta 2. Okay, if this is the way we want to represent, then we have to find out the value of n1, n2, n3, n4. What we also notice here is, if we have u defined like this one, we can also find out theta. The theta as a function of x will be du over dx, and that will be equal to dn1 dx multiplied by u1 plus dn2 dx theta 1 plus dn3 dx u2 plus dn4 dx, this will be theta 2. Okay, so or we can also write like summation format. So theta x equal to du over dx is equal to summation of I equal to 1 to 4 dni over dx di, where di is as given here. Okay. Now once we know the expression for u1, ux and theta x, next thing is how to find out n1, n2, n3, n4. So for example, if you see ux, what you know is when u equal to 0, x equal to 0, so u at x equal to 0, that has to be equal to u1. Okay, then this is one constraint that we has to be satisfied by u. So value expression for ux is given here, but this is subject to u0 equal to u1, then ul is equal to u2, then du over dx x equal to 0 is equal to theta 1, and du over dx x equal to L is theta 2, or we call it d1, we call this d3, we call it d2, this is d4. So these conditions also has to be satisfied. Okay. However, u is a function of n's, right? So for example, u0, if you write u0 equal to, since this is a summation of nix, since ux equal to summation of nix di I equal to 1 to 4, so we can expand. That really means u at 0 has to be equal to summation I equal to 1 to 4 ni0 di. Okay. Now we know that d0 equal to d1. Okay, so that really means what? That really means this tells us n1 0 equal to n1 0 equal to 1, and all others will be 0. So n2 0 equal to 0, n3 0 equal to 0, and n4 0 equal to 0. And similarly for all of them, all the x's, other x, for example at ul, for example ul is equal to I equal to 1 to 4 ni L di, and that only tells us that since d3 equal to u4 2, so this is equal to u2, so u0 equal to u1, and we know that d3 is equal to u2, so that really means only n3 will be 1. That tells us that n1 at L is equal to 0, n2 at L equal to 0, n3 at L equal to 1, and n4 at L equal to 0. So this set of equations we have now. For others we have to write in the expression for theta. So as we know that theta x, we can write theta x equal to nothing but summation, this is same as here, this equation we are going to write. So theta x equal to dn I dx, okay, and here this will be di summation I equal to 1 to 4. Now theta x, let's examine at x equal to 0. So theta 0 will be equal to I equal to 1 to 4 dn I dx at x equal to 0 times di. Okay, and that we know that this has to be equal to theta 1, because at theta 0 theta is 1, so theta 1 value is there. This is only possible when that tells us that dn I over dx x equal to 0 equal to 1. Okay, all other places, because di sorry, theta 1 is d2, theta 1 is d2, so that really means dn I dx x equal to 0, that should give us equal to 0. Okay, and dn n1, okay, and here dn2 over dx x equal to 0 should give equal to 1, because this is because theta 2 d2 equal to theta 2. So that means d2 equal to theta 2. So d2 is being multiplied by n2 here, dn2 over dx. So hence dn2 over dx as at x equal to 0 has to equal to 1, and all others will be equal to 0. So this is dn3 over dx x equal to L equal to 0, and similarly dn4 over dx x equal to L equal to 0. So this is x equal to L has to be equal to 0. So same thing we have to repeat for the last for theta 2. So we have theta x as a summation of I equal to 1 to 4 dn I over dx and di. Okay, so theta at x equal to L, we know this is equal to theta 2. Okay, this is equal to theta 2, and that is equal to theta 2 is nothing but d4. Okay, so this is equal to I equal to 1 to 4 dn I over dx. This is x equal to L and di. So looking at it, you can guess that similar to the things we have been doing. So dn1 over dx at x equal to L will be equal to 0. Similarly dn2 dx dn1 dx at x equal to L equal to 0, and that's correct. dn2 over dx x equal to L is equal to 0. dn3 over dx at x equal to L will be 0, and dn4 over dx x equal to L has to be equal to 1. Okay, since dn4 over dx is equal to 1, that's why this is multiplied by d4 becomes theta 2, and hence this expression is valid. So we got one set of constants here as well. So let's look at now look at n1 only. Okay, so we got four set of constraints, and all of them have n1, n2, n3, n4, which is evaluated at different x. Okay, so now if we just look at n1 in all the four sets of equations, we have n1 at x equal to 0 is 1, n1 at L equal to 0, then dn1 over dx x equal to 0 is equal to 0, and last is dn1 dx at x equal to L equal to 0. So let's summarize it here. So the requirement for n1 is n1 at 0 has to equal to 1, then n1 at L is 0, dn1 over dx calculated at x equal to 0 is also 0, and dn1 over dx calculated at x equal to L is also equal to 0. So we have to find out this one. So that means we have n1 which has four equations basically at for different 0 and also for 1, this is without derivative, this is with derivative. That means we have four equations, so there has to be four unknowns that has to be found out. Okay, so that means you can guess the we can write n1 x as a cubic function also. So we can write as alpha 1 plus beta 1 x plus gamma 1 x square plus delta 1 x cube. So n1 will be of this form. So in order to find out alpha 1, beta 1, gamma 1, delta 1, we have to put these values. Okay, so before we put the values, we can also take derivative here. So dn1 over dx is equal to beta 1 plus 2 gamma 1 x plus 3 delta 1 x square. So this is dn1 over dx. So we have this one. Okay, now we put these values, these constants we apply. So what we get is n1 0 equal to alpha 1 plus all those 0 becomes equal to 1. So we get alpha 1 equal to 1. Then we put the this value. Then we have dn n1 dn1 over dx x equal to 0 is equal to, so here the value is, so what we get beta 1 plus equal to, so that makes it beta 1 equal to 0. Similarly n1 L is equal to, so this becomes alpha 1 plus beta 1 L plus gamma 1 L square plus delta 1 L cube, everything that becomes equal to 0. And similarly dn1 over dx at x equal to L equal to beta 1 plus 2 gamma 1 L plus 3 delta 1 L square is equal to 0. Okay, so we already have alpha 1 beta 1 here. So alpha 1 is 1, beta 1 is equal to 0, so we can put values here. So finally what we get is there are only gamma 1 and delta 1 are unknowns, so we can solve these equations after putting values of alpha 1 and beta 1 here, and you can also find out the value for gamma 1 and the delta 1. Okay, so this can be repeated for all others n, so for n2, n3, n4 actually. Yeah, so we can also write the in matrix form. You can write, and the equation will be something like this. So we have alpha 1, then beta 1, gamma 1, delta 1, and what we have is 1, 0, 0, 0, and what do we have? We have 1, then 0, 0, 0, 0. Okay, the second one is we have 0. So second equation was this one, this equation. So here we have value of 0 here, so we have 0 plus 1 plus, so here we have 1, then we have 0 and 0. Okay, then we have 1 here, then we have L square, L cube here, and here we have 0, then we have 1, then we have 2L and 3L square here. So this equal to this, so you can find out, solve it to get alpha 1, beta 1, gamma 1, delta 1. So similarly you can find out for others. So if you know delta 1, beta 1, gamma 1, delta 1, you can find out the n1. So n1 will look like this one. Similarly, you can propose in general ni x equal to alpha I plus beta ix plus gamma ix square plus delta ix square. So in general you can write it like this one, and you can find out, follow the above method to find alpha I, beta I, gamma I and delta I. So this is not new. This we can actually this we have seen already. So wherever you wanted to find out the shape function, we have the shape function, then we have the constraint applied, meaning that we know its values at certain nodes, and based on that we find out the coefficient. The same thing we are doing, but you know that this way it takes a lot of time, so we will find out a shortcut to do it, okay, as we have done earlier as well. We will find out the shortcut in the next lecture video. So here we will just see, if you really want to solve in this method, then what will be the other equation which will solve alpha I, beta I, gamma I and delta I. So this is for finding out alpha 1, beta 1, gamma 1, delta 1. For finding out alpha 2, beta 2, delta 2, gamma 2, delta 2, this will be simply, so this equation actually remains the same. At the left side will be the same. So this will be 1 0 0 0 0 1 0 0 0 L L square L cube and 0 1 2 L 3 L square. So you have that, and here multiplied by you have alpha 2, beta 2, gamma 2, delta 2, and this is equal to, this will be equal to 0 1 0 0 in this case. So you solve this problem, you will find out that. Okay, next thing will be 1 0 0 0 0 1 0 0 0 L L square L cube, then 0 1 2 L 3 L square, and you have alpha 3, beta 3, gamma 3, delta 3 is equal to 0 0 1 0 in this case. Okay. Now let's see here the last one, the last equation, 1 0 0 0 0 1 0 0 0 L L square L cube, 0 1 2 L 3 L square. Okay, and then we have alpha 4, beta 4, gamma 4, delta 4, and is equal to 0 0 0 1. Okay, so we have this equation, and we can, based on this, we can find out alpha i's, beta i's, gamma i's, delta i's, and hence you put this value here and you get all the 4 shape functions. As I said earlier, this can be done in computers very easily. However, if you want to do manually, then this will again is time taking. You can do it of course, but it's time taking. So we will see the shortcuts. Okay, that will be in the next lecture video. Okay, thank you. Before I end the lecture, so I want to point out to some corrections. So if you see here, the first matrix we have 1 0 0 0 1 0 0 1 L L square L cube, and I said same matrix has to be repeated here, but if you see here we have an error here. So instead of 0 it should have been 1. Okay, so I will just correct it to 1, and all of them will be like that. So third row should be 1. Okay, so all matrix, third row, the first column has to be 1, third row first column has to be 1. So I have done this here. Also here while finding while writing down the equation for the theta x, so here by mistake I wrote d2 equal to theta 2. Actually d2 has to be equal to theta 1. Okay, so this correction please note. Okay, now see you in the next lecture video.